So we were discussing small signal model for a two-port network, right? We started off with a very brief overview of whatever we have done till now. We essentially said that we cannot live a life without the use of nonlinear elements. So since we need a nonlinear element, we may as well understand how to figure out how to go about analyzing them without going into brute force algebra. And as it turns out, in most cases, brute force algebra will also not give you a very closed form solution because anything more than third order, there is no generic solution for any polynomial equations, right? So we had to resort to some sort of approximations. One such approximations was small signal approximation, where we essentially say that if we understand things are nonlinear. By nonlinear, if I have to explain nonlinearity to somebody who is not in college, maybe in school, what would I say? I would essentially say that nonlinearity means if you have a transfer function, if you have a function, if you have a black box which the input and the output are related by some f of x, then if it's a linear function, then for every equal increment at the input, they will see some equal increment at the output, right? So that's essentially nonlinearity is. Linearity is, right? If you change the input by 1 volt, the output maybe changes by 2 volt. But if I even change the operating point and I change the input by 1 volt, still the output will change by 2 volt, right? For every increment at the input, regardless of when you do it, where you do it, which point of the curve you do it, the output change will always remain constant. But if that is not true, then it's a nonlinear function. So this is quite easily understandable. But then what we do with this understanding? So what we essentially say is that what Taylor series essentially gives us a framework that we understand that even though equal changes in input will not lead to equal changes in output all the time, or rather everywhere in the curve. However, if I limit the observation to certain vicinity of the curve, then it's possible that within that vicinity of the curve, I can approximate the curve to be like a straight line. And if it's a straight line, then again we fall back into the approximations of, or we fall back into our knowledge of linear equations, sets of linear equations, which essentially means if we apply equal changes of input, you will get equal changes in output. That's essentially is a small signal approximation. Can we be within that small vicinity of a nonlinear curve, or small vicinity of a point in a nonlinear curve, so that approximation by a straight line will not lead to too much of error, right? So we did all these things. We developed a mathematical framework. Then we saw that if I give you a generic IV nonlinearity, how would you express that? If everything is resistive, we can simply say that if I have a nonlinear element, it will have some quiescent I, quiescent V, or operating point I, operating point V, or biasing point I or biasing point V. All of the above mean the same. In that case, I can replace that nonlinear element with a resistor of value 1 over del I del V, where del I del V evaluated around the operating point. So by doing that, we found that if we have a diode, I can replace the diode with, to do the algebra, as it turns out, you can replace a diode with forward bias diode with VT over ID, where VT is a thermal voltage, ID is a quiescent current. But if you have a generic nonlinear element with some function f of V, then I can replace that element with 1 over del F del V, right? So you did in the last question set, there were some generic nonlinear elements. Some of them had different square characteristics. Some of them had exponential characteristics. And when we and I'm sure all of you have gone through the assignment. There was a quiz also. So now that we have the framework, what we wanted to do next is to see that if we have to design an amplifier, right, which ultimately amplifier is the goal of this course. If we have to design an amplifier, then we took a step forward and said that it's not only the fact that a nonlinear element we cannot live without, everything is nonlinear. As it turns out, nonlinearity becomes essential to realize power amplification. right? So we went through a couple of lectures to understand why it is necessary. So now if we require nonlinearity to get power amplification, and in order to get a power gain at a certain port, then we need to then figure out a framework to analyze at least a two-port network, because when we are talking about amplification, we are talking about amplification between at least two ports. So we talk about a two-port network. Now that two-port network, we again consider it to be a generic nonlinear two-port, right? So when we consider it to be a generic nonlinear two-port, again, we got stuck with the same problem. But now we have a framework, so use the framework of small signal approximation, and we then came up with a linearized two-port network. A linearized two-port network, a model of the linearized two-port network, we considered that was to be a two-port Y-parameter. We came up with a model which can be modeled like a Y-parameter matrix, incremental two-port Y-parameter matrix. And what is so great about incremental two-port Y-parameter matrix? It is completely linear, right? So now again, we are in that linear zone. The whole purpose is to get into the zone that we understand, right? Not in the zone that we don't understand. So linear networks we understand. So we came up to, so we essentially said that, so now a generic two-port network can be modeled like this. Where this is the stuff inside the box. And now it depends on us how we connect the input, how we connect the output, and so on.
So,
yes.
We started with simplification of black box. You also had VDC and IDC. You had also shown that in the diagram.
Right.
Now,
right. Yeah. So yeah, his question is, when we started off with a black box of generalized nonlinear network, we also had VDC, right? So that would have been my question here, right? So why the VDC was required in order to ensure that we power up the system. By power up, I mean that we also, the stuff that I missed in the recap was, we also established the fact that you cannot get power amplification by simply connecting an input or the output, regardless of the fact that you are using nonlinear network. You need another power source, because simply power conservation has to hold. There is, in principle, there is no power amplification, just that you can transfer power from somewhere to somewhere. So in this case, we saw that we need to transfer power from a DC source to a AC. To a AC signal ring, right? So for that we require a DC source. So now the question is, where has the DC source gone in this model, right? That is his question. Can any of you give a shot at it?
It was for 2 point.
Right. So it is for Q point. Essentially, what is the now if we consider the DC source, what is it essentially doing? It is setting up the quiescent INV, right? So now question is, which parameter in this two-port network is getting influenced by the DC source? The Y parameters, right? Because Y parameters are dependent on the quiescent INV, right? The differentials of the quiescent. So even though DC source is not present in this picture, but it's hidden inside the values of the Y parameters. Okay. So as a designer, when you think, you might want to think that we also saw that the gain is dependent on Y parameters, right? So let's say I design a circuit, the gain is not good for whatever reason. I want higher gain. So then I have to change the Y parameter. But what is the handle that I have? VDC, right? VDC, or we'll see, we'll have many more handles going forward, but VDC is one of the handles, because VDC is influencing our biasing point. This directly influencing our Y parameters. Okay. Okay, great. So then we also did this bunch of algebra, and we saw that there is certain relationship between there is a wish list. I shouldn't say relationship. There is a wish list that a designer has in order to get high voltage gain. Now we are talking about only high voltage gain, because we understand that the voltage we are taking is across RL. So if I get high voltage, I will naturally get high power, right? So we can now talk about voltage gains. So if we get high voltage gain between V2 and Vi, then our purpose is solved. And in order to get high voltage gain, what did we see? We saw that after doing a bunch of maths, we saw that all we need is to ensure that Y21 is as high as possible, Y11 is as small as possible, Y12 shouldn't be there to prevent oscillations, and Y22 should also be as small as possible. And we saw that using some sort of maths. I mean, we jumbled up maths with, heuristic reasoning. But essentially, what we are trying to say is that why do you want Y12 to be 0? We want Y12 to be 0 because we want to stop unwanted feedback from output to input. Because if there is feedback, unwanted feedback, right? The unwanted is the key word. If there is unwanted or uncontrolled feedback between the output and the input, then it is possible that under certain condition, you might end up with positive feedback and your system can oscillate, right? So that's why we wanted to get rid of Y12, or rather we wish Y12 to be equal to 0, right? This is the wish list. Then also we said that Y22 should be, ideally should be equal to 0. Why? Because ultimately this current that is coming out in the opposite direction, in this case, the current that is coming out is getting divided between two resistors, the ultimate load resistor and the Y22. Now, Y22 is not an exact resistor. It's a model resistor, right? It's not as if you are seeing an exact resistor of Y22 in your network. It's a mathematical model, right? It's an incremental resistor. It's often called an intrinsic resistor to the system, right? It's an intrinsic output resistance, right? So if this if the incremental current gets divided between this intrinsic Y22 and the final RL, then naturally I am losing some part of the power into this intrinsic. Some part of the current is flowing into the intrinsic resistance and not into RL. So ideally, we would want Y22 to be 0, right? And similarly, if I turn our attention to the input side, Y11, ultimately we see that this current Y21 V1, we want it to be maximized in order to get large output power, right? Now V1 is what? V1 is the voltage that is accruing across the input port. So now if the V1 is that voltage, we would like to have V1 to be as high as possible. The maximum V1 that is possible is Vi only when Y11 is 0, absolutely 0, right? If there is some non-zero Y11, V1 will drop from Vi. So we don't want that. Again, it is a wish list. It's not as if it's going to happen just because you wish it, but this is something that we would like to have. So now, yes. Yes. When I write Y, it means conductance. I don't want to write 1 by every time. So that is okay. So now that what essentially we end up with our wish list for a two-port network, an ideal two-port network, ideal incremental two-port network is this. So it should essentially look like this. Right? So this is an ideal two-port network, which will give us decent power amplification. Right? This is our wish list. Now, we all understand that this is not possible, right? Because nothing is ideal. Just like you cannot get anything to be 0, you cannot get anything to be infinite. So similarly, I mean, it's not as if Y11 can actually go to 0 completely, or Y22 can completely go to 0 always. In certain cases, maybe it can. In most cases, it cannot. So if that is not possible, now we know under what conditions this might work, right? Or this might not work. So let's say Y22, or let's say 1 over Y22 is not infinite. Y22 is not 0, which means 1 over Y22 is not infinite. Can you comment looking at the output port under which the output port behaves like what we want? So question is, in principle, you cannot ever get Y22 to be equal to 0 in a practical circuit, right? The reasons you will see later on, right? So, but whenever I say it is 0, at the back of your mind, you should always think that just like you cannot get infinity, you cannot also get 0, because they are 1 over, right? The flip side of the same coin. So if this is not 0, which means I'm always going to get some division of current. So I'm losing some amount of power. So yes, I will always lose, but under what condition this will behave like a better amplifier? Right, exactly. RL is much less than Y22, 1 over Y22. Right. So essentially, it will behave as long as all the current gets diverted into RL, or most of the current gets diverted into RL, and it doesn't flow into the intrinsic resistor. Okay. Similarly, at the input side also, it will behave like a very good amplifier as long as the input resistance, right? So this resistance 1 over Y11 is much higher than ours. So again, you see that it's not as if just because you have a box, you connect anything to it, it's going to work. You have to honor the loading effects, right? So that is something that you have to be mindful of. Okay, fine. So now let's proceed. So now that we understand, at least in the incremental sense, what are the requirements? So the whole purpose of this is to design the final nonlinear block. Right? It's not like we can stop the course just because we understand what are the requirements of a Y parameter. Ultimately, Y parameter is a model, but as a designer, you cannot give a model to the user. You have to give a full block, right? So which means that we need to understand what type of IV characteristics, the actual total IV characteristics, not the differential, not the incremental. The total IV characteristics should look like when we want to design this entire loop. Okay, so let's now take a step forward, right, and then see how can we build up the IV characteristics of an actual amplifier, or IV characteristics of an amplifier that we would like it to have. Okay, so let's see. So let's start off with the first one. So we have 4 parameters. One is Y11, Y12, Y21, Y22. So what is Y11? Y11 is del I1, del V1, when V2 is equal to, or rather, del V2 equal to 0. Right? So if I have to find out, or rather, from which IV plot can I get this information of Y11? Because I have 2 ports. I have 2 sets of currents, 2 sets of voltages, right? I have I1, I2, V1, V2. Essentially, I can have 4 plots, right? I1, V1, I1, V2, I2, V2, I2, V1. I can have 4 sets of plots. So which plot should I look at in order to get Y11? I1, V1, right? So let's see. So I should plot I1, V1 under the condition that V2 isn't changing, right? Delta V2 is 0, which means V2 isn't changing. Or in other words, I can say that V2 is constant. Let's say V2Q, right? Under the condition V2 is V2Q, what should I1, V1 look like? So now our expected Y11 is 0, which means, can you comment on what should this plot look like? I1 should be constant, correct? So I1 should be constant. So now, so let's say constant means I draw a straight line parallel to the x-axis. So can you comment that this I1 should be constant? Let's say I call this I2Q or I1Q, sorry. I call this I1Q. Should it be constant across all values of V1, or should it be constant, let's say, around V1Q? It should be around V1Q, because that's all we know, right? We want the differential to be 0, but we want the differential, I mean, all we can derive from this argument is the differential will be 0 around an operating point, right? That's all we know. However, since we are preparing a wish list, right? Since we are preparing a wish list, we can extend that argument and say that if this is 0 around only 1 point, then it's probably not a very good amplifier, right? Because I would want a range of V1Q for which I should be able to use it as an amplifier. Okay. So that is, if that is true, then what we need to do, what we not need to do, what we wish for is a range of voltages for which this is constant, right? So this is a wish list again. So this is probably, this should be constant, right? This is again a wish list. Can you also comment on what would happen if V2 is equal to V2Q, or rather, sorry, V2 is, let's say, V2Q, I shouldn't say dash, it's a V2, but some other notation. So V2Q2. Okay, so I changed the output quiescent voltage. And I would like to draw the same plot. Again, do you expect the I1 versus V1 plot, the new I1 versus V1 plot to overlap? Is it necessary that it overlaps? No, right? It can be another plot, but as long as it is flat, I am good, right? So it can be something like this, right? So that's all right. I mean, this is something that we want, right? This is expected. Okay. So then now let's move again to Y22. Y22 is del I2, del V2 when V1 is constant, but delta V1 is 0. So we'll do the same thing in this case. So just like I1 V1, this I2 V2 plot could also look like this. It should be constant, and it should be constant across a range of, this is V1Q. It should be constant across a range of V2 with following the same arguments that we followed for the I1 V1 characteristics. Let's say we have another, we change V1Q voltage, so V1Q2. So maybe the plot of I2 versus V2 shifts to some value, but as long as it is flat, we are still not violating our requirements. Okay, okay, great. Now, same thing with Y12. What is Y12? No, what is the expression? Del I1, del V2, while del V1 is 0. So what should I plot? What should be the x-axis, y-axis? I1 versus V2, great. Again, same arguments, right? So no change. So this is when V1 is equal to V1Q. I'm not drawing the other curves, so it's essentially this. Now let's come to the only different plot, right? That is Y21. So Y21 is del I2, del V1, when del V2 is 0. Okay, so again, what should I plot? I2 versus V1. And let's say plot around some operating point. This will be around V1Q and some operating point of V2Q. So what should it look like? For an ideal amplifier, what should it look like? Again, let's go back here. Yeah. So if I look at this, incremental network, Y21 is the core of the amplifier, is the heart of the amplifier, right? That is relating the information between the input port and the output port, right? So whatever input port voltage it is accruing across V1, that is getting transferred to the output port through this incremental network Y21, incremental voltage control current source Y21, right? So a very interesting question came up after the end of the class day before yesterday. Let me ask you this question before I proceed. The question that came up was, this network is LTI, right? This network is LTI. Everything is linear. So now I am saying that using this network, I'll be getting power amplification, but we started off a few lectures back while we said that LTI system cannot give you power amplification. So where is the dichotomy? What's happening? Am I contradicting myself? Right. So his point is it is an approximate network. That is true. It is an approximate network, but there is a deeper meaning to it. So deeper meaning is, when I said that you cannot get power amplification using LTI network, that is not a full statement. The full statement should have been using the devices that we already know of. That is using RLCs. right? Or even, I mean, any other linear device that might exist, right? If tomorrow or maybe a few years from now, somebody comes up with a novel linear device, right, which nobody has seen, I don't have to even look at the characteristics of the device. I can tell you that it's a linear device. It cannot be used for power amplification. Okay, so that's all it means. But then how come this is a linear network? How come this is giving power amplification? This is giving power amplification because this guy doesn't exist in reality, right? You don't have a linear voltage control current source. It doesn't exist. It exists in the incremental domain, but it doesn't exist in the natural domain. Because the way you should think about it is, this Y21, V1 seems like a generator. It's a source. It's a voltage control current source. It's fine, but it's still a source. From where is it getting the power? It's getting the power from the original network, right? It's getting the power. The information of the power is embedded in that VDC, right? Which was there in the original network. To take away VDC, this Y21 will go to 0. Because ultimately, no current, I mean, if the quiescent I and quiescent V are 0, I mean, all differentials also go to 0 essentially, right? So you probably will not be able to get anything. Okay, so it's not as if this, even though this looks like an LTI network, this is an LTI network, but it's an LTI network which is in the incremental sense. You don't have such an LTI network in the in a total IV sense. That's not possible. Okay, fine. So now that we understand, now that we were looking into the IV characteristics of these networks, so what is the expected Y21? The Y21 should be as high as possible, ideally infinite, right? So if Y21 needs to be as high as possible, then what should I2 V1 curve look like? It should be steep, right? It should be steep. It should probably look like something like around the operating point. It should look like this, right? And again, using the same logic that I gave earlier, that it's not like I would want it to be steep only at one small operating point. Since we are developing a wish list, I can as well extend the wish list and say this should be steep for a range of V1Q. Otherwise, our device will probably not work well if I just change V1Q, right? So it should probably look like this. And this is for a particular V2Q. If I change V2Q, let's say I say it goes to V2Q some, then again, I probably will probably get something which is something like this, right? So now it depends, right? Now it depends on the type of nonlinearity, but we would also not want the device to have this steep slope for only one value of one parameter of V2Q, because ultimately we know that everything is liable to change to some extent, and your temperature will change. You probably will be using it a day. I mean, sometimes even if you check Kanpur climate, sometimes it will go to 45 degrees, sometimes to almost 0 degrees. So you'd like to, you would want your devices to work across the range of temperatures, right? So essentially, it's not like, even though I haven't talked about semiconductor physics and how things change, but we should at least appreciate the fact that if your temperature, humidity, and everything changes widely, you cannot expect everything to remain constant. So characteristics change. IV characteristics tend to change. So because they tend to change, you don't want to have a device which works very well only at any small bias point, around a small bias. You would like to have some leeway. Okay, fine. So this is as far as the desired IV characteristics of a two-port network is concerned, right? So this is still a wish list, right? We haven't yet figured out whether this is a possibility. So now the fact that I am spending so much time on this means that it is possible, right? So people have been working at it for centuries, right? And you will see that there are devices which actually give this type of characteristics. For example, I'm sure you have done this in ESC 201, BJT, bipolar junction transistors. They have IV characteristics which are similar to this, right? If you don't recall it, okay, we'll get to that when the time comes. But if you want, you can revise your notes of ESC 201. Similarly, there is a device called MOSFET, right? So acronym for metal oxide semiconductor field effect transistor. Again, you don't have to recall all these things. this, I mean, BJT, MOSFET, if you go back, way back in time, there will be cathode ray tubes. If you talk about present day devices, which are also being used, but not so much in analog circuits, but probably will be used in another 5 years or so, they are called FinFETs. And there are some other types of devices called gate all around MOSFETs and so on. So essentially the message that I'm trying to give you is that if you look into the IV characteristics from the lens that we just talked about, you will see that all of them have IV characteristics similar to this in certain ranges of I and V. Not all through, but in certain ranges of I and V, you are going to see IV characteristics similar to this. And it is not by accident, it is by design. Right? So you can make infinite number of types of devices with infinite types of IV characteristics. But why are people inclined to make devices which have IV characteristics like these? Because they help in making amplifiers. Okay. So now the question is, I mean, I cannot basically take the course with all these devices. You have to choose one. So I have to choose a vehicle to explain everything, right? So the vehicle of choice for this course will be MOSFET. Why? Because overwhelming majority of analog circuits in today's world is made using MOSFETs. There is some part of analog circuits still which are made using BJTs, but the overwhelming majority is MOSFET. And since we established the fact that the principles are same, right? The principles from which we derive the IV characteristics are essentially same, which means that going forward, the analysis will also be same. I mean, at least similar, if not same. So if we understand one set of principles to approach designing circuits using one vehicle, right? So it's like you know how to ride one bicycle of one company. I mean, it's not like you have to learn all together again if you change the brand of the bicycle, right? It's basically that. So I am using the brand of MOSFET to show you how analog circuits, you can go about designing analog circuits. Then at the back end of the course, in last 3 or 4 lectures, we'll move into BJTs, right? So and one of the reasons we'll be moving into BJTs is because BJTs are not only used in today's world in certain segments, but also the labs that you are going to do, 380 labs, 381 labs, you'll be using BJTs, right? So you need to understand how BJTs work and what are the certain nuances, what are the certain differences between MOSFETs and BJTs. But you don't have to worry about BJT till then. We'll be using MOSFETs. Okay. Okay. Any questions till now? Yes. Okay. Very good question. So he's saying the graph of white function pass to drawing. Why do you say so? Right. So it's y equal to mx linear relationship in which domain? In total IV domain or in incremental domain? Right. But this is not an incremental domain. Right. So when you say it should pass to the ordinary incremental domain, there is a lot of assumption going into it. First is the linear domain, but there is also shift of axis. Right? I am doing when I am doing a differential, I am simply saying I am drawing a tangent. Right? And also I have shifted the axis there. Then and only then it will pass to the order. Right? So that's what essentially happens, right? When you do a small analysis, we not only do a tangent, we also inherently get the assumption that in the incremental domain, there is everything is, I mean, moment you do incremental, you are putting the origin around the opposite. Okay. So that is, I mean, if we approach these analyses from the perspective of coordinate geometry, that's what we do, right? But we don't want to approach it using that manner, so you didn't want to specify that. But very good question. Okay, fine. So let's. So what I will do is for this whatever 10 minutes we have in this in today's lecture and the lecture on Friday, I will give you a brief introduction into a very rudimentary introduction into device physics. Right. So I hope, I mean, I understand you guys know about electrons, holes. You know that, right? I mean, from your class 12 days, I presume it's already a part of the world. Right? You don't need to do any mathematics on this, right? So this will only be storytelling. But The understanding should be that at least you know how these devices work, right? At least in the sense of developing an intuition. Okay. Do you know about PN junctions? Do you know how PN junctions work? Forward bias, passing, negative, reverse bias. Fine, great. Makes life easier. So we'll use those concepts of. Do you know what? Do you understand doping? Okay, great. So trivalent impurities, pentavalent, so on. So p-type doping, n-type doping. So we'll use those knowledge. We'll use those knowledge to develop a device, right? It's not as if I am developing a device from scratch. I already know people what type of devices they are. So I'll try to relate the intuitions that we have to the devices that are used, right? So if I make that relationship, then probably it will be easier for you to appreciate why the devices work like why they work as if they are the perfect devices for getting amplification, right? So we'll do that for whatever time we have in today's class and better part of the next class. But even before getting there, let me give you an analogy, a very rudimentary analogy, a mechanical analogy of what an amplifier is. Okay. So the reason I'm doing that is it will help you in relating a mechanical amplifier to an electronic amplifier. So now we at least know that this guy is this is a two-port or at least a 4-terminal device, right? It's a 4-terminal device. I can as well say that it might be possible, even if I short these two nodes internally, if it is possible to short those two nodes internally as I show, it still probably is possible that I get an amplifier, right? I still have 2 ports, just that one of the terminals of the ports are connected. Okay. So let's have that in the back of the mind. Not required right now, but let's have that in the back of the mind. So let's say I have a water tank, right? I have a water tank filled with water, and there is a pipe that is coming out filled with water. Maybe I'll make it a bit wider. And this side of the pipe, when the water is gushing out, you have a spring attached to it, right? And the spring is maybe connected to a load. Okay. And here you have a piston, right? So this is somebody. Pardon? This is a mass, some mass. Okay. So you don't have to bother about what it is attached to. Maybe it is attached to some quiescent something, right? It can move up and down. It is held up with something, which is mechanical equivalent will be some, I don't know, quiescent wall, right? So, fine. So now, so let's say somebody, I'm sitting here, and what I am doing is, and this is movable, let's say, this is movable in the horizontal directions. Okay. So what I do is at times I take it and move it all the way here. And at times I move it all the way back. Right? So can you comment on the flow of water that is coming out? This is an infinite reservoir, right? I don't want you to go into the details of solving equations, right? So what is the intuition? What do you think will happen? If I move this piston all the way almost to the edge, right? So the flow of water will reduce. And if I pull it back, it's going to increase, right? So essentially, and maybe let's say this is a 1 centimeter dia, right? This is a 1 centimeter dia. So how much am I moving the piston? Maybe maximum 1 centimeter to 0, right? Within that 1 centimeter range, I'm moving the piston. But depending upon what is the flow of force of water, this mass can move up and down by a large amount. Obviously, depends on the time. I don't remember what it's called. Time constant of the spring. K. What is spring constant? Spring constant of the spring. Depending upon the spring constant of the spring, spring, it can go up and down by a very small amount or by very large amount, right? So if I define amplification as delta y here with respect to delta x here, then del y over del x is more than 1, right? So that's a mechanical amplifier, right? Makes sense? So I am imposing, I'm probably moving, I'm probably moving the piston by 1 centimeter, but I am getting a movement of maybe 1 meter or half a meter or something, depending upon what K of the string is and what the mass is. And so that ratio of the differential is clearly more than 1, or can be designed to be more than 1, which means this is a mechanical amplifier. Make sense? Okay, so what is the electrical analogy of this? The electrical analogy of this is, if we can, let's say, again, we are in the if domain still now, we don't know what it is. If we can make, what is the equivalent of a reservoir in electronics? It's a voltage source, right? So let's say I have a voltage source. Let's say I have a resistor, and I'm interested in the voltage across the resistor, right? So let's say, just like a pipe, maybe I have a conductor, right? So current flows from top to bottom, right? So what do I need to do in order to get an equivalent application with respect to the mechanical equivalent? What do we need to add? A third terminal at least, right? So this is another terminal. So I am abstracting the flow of water from a third, not in the, I mean, the control source in this case is not in the path of the flow of water, right? The control source is somewhere else. So I am the control source who is moving the piston orthogonally. So similarly, you will need a control source in an electrical equivalent, which can modulate this, I shouldn't say cross, which can modulate this flow of current, right? In this case, I was modulating the flow of water, right? So in this case, we have to modulate the flow of current. So when I say modulate the flow of current, essentially I'm pointing out the fact that I have to modulate the amount of charge there is in the conductor. Just like here, you are modulating the amount of water in the region between the piston and the pipe. So I need to have some handle which can modulate the amount of charge that is present here. If I can modulate that, and then I put a time variance to it, right? So I keep on changing that amount of charge, then it is possible the amount of current that is flowing into the resistor will also change incrementally, then I can get a gain. Does that make sense, or am I speaking gibberish? Makes sense. Okay, good. So now can you tell me what type of, from whatever knowledge you have till now, what type of element is there that can modulate a charge? You said something? Resistor in parallel will not modulate a charge, right? I mean, it can change. So what you are essentially saying is that I have to change the value of the resistance, right? So I don't want to get into that. Changing value of the resistance means you have multiple resistance, you change from one to another and so on, right? So I don't want to change the characteristics of the circuit. Changing the value of the resistor is changing the characteristics of the circuit. Capacitor is one thing that holds charge. If I change, now in order to change the charge of the capacitor, I don't have to change the value of the capacitor per se. I can change just the voltages, which is in my control, right? So if there is a capacitor plate here, which can, I apply, let's say, a changing voltage here, which can change the charge on the other plate. Then I use that charge, and then I use this modulating charge, and I pass it through in the direction that I want. Then it is arguable that it's possible to make a device which can give us a modulating, incrementally it can give us some amplification, voltage amplification. Right? Make sense? Right? Okay, but the issue is, if you use a simple metal plate, right? A simple metal parallel plate capacitor, if this is an ideal metal, yes, you will be able to modulate the charge, but you will never be able to deplete the metal of its charge, right? So if you cannot ever deplete the charge there, you will not be able to change the current that is flowing from top to bottom. Right? You'll probably be able to change the potential of that on the surface of the metal plate. But since this is almost close to an ideal metal, the charge content on this, I mean, moment you put a voltage source between these two terminals, it doesn't matter what type of transverse electric field you have. The amount of charge that will flow from top to bottom will only be dependent on the vertical electric field. Right? So you'll not be able to get that control, even though the principle is understandable, but you'll not be able to get that control. So semiconductor physics comes in there. So semiconductor helps you in getting that control. Okay, so we'll start with that in the next class.